Okay, here's one of the equations that we solved at the beginning of the class. And again, this is like last exam, except notice that we have an issue here. We need to get everything in terms of sine and cosine of theta. And so again, in trig, we use identities to get rid of this stuff. So there is a trig identity for double angles, and for sine, there's only one choice, which is really awesome. Cosine, you have three choices, so you got to think a little bit harder, but here, not so much. So this one right here, I can instead write 2 sine of theta, cosine of theta, and that's because this trig identity goes together, and so everything else was fine, so that I don't have to deal with. All right, now, typically we try to factor these, and notice there's 1, 2, 3, 4 pieces, and so the way we factor things that have 4 parts to them in algebra is we do factoring by grouping. So we take the GCF out of these, so the greatest common factor is sine of theta, and what's left is that, and then we take the greatest common factor here. Now, you have to at least take out a positive one or negative one. You can't take out nothing. So here, notice I want the 2 to be positive, so I need to take out a negative 1. And so then the 2 becomes positive, and that 1 becomes negative. Now, if factoring grouping is going to work, after you take out the greatest common factor, then these guys are going to be in common. So that's your new greatest common factor. So you have a GCF of those, GCF here, and then after you do that, these should be in common. If not, it's not factorable. So you're going to pull out that greatest common factor, and then your leftovers go in the other blank. Right? And again, you only have one of these out here because when you distribute it, you give one there, and when you distribute it, you get one there. So sometimes people are like, why isn't this squared, or why don't you have 2 of them? Well, you know, it's because you do it twice. So you distribute it there, and you distribute it there. All right, so now you have it factored, so you set each piece equal to 0. So you set that one equals 0, and that one equals 0. Bring the 1 over, and divide by 2. So you get cosine theta equals 1/2. Here you bring that over to the other side, and you get that. Now again, at this point, you're going to do the inverse function to both sides. So I'm going to do inverse cosine, those are going to cancel. Inverse sine, those are going to cancel. Right? And here you're going to get theta equals the inverse cosine of 1/2. Now, if those aren't on the unit circle, you're going to have to do radians, and you're going to have to figure out both values in radians. If they're on the unit circle, then you should be able to look at it. So here I have 0, 1. 0, -1 isn't going to cut it, so there's actually only 1 point. That's kind of unusual. Usually there's 2 points for all of these, but this time there's only 1. And so theta is at pi over 2. And then every coterminal angle with that. So plus 2k pi is going to give me the rest. This one I want cosine of 1/2. So 1/2 square root of 3 over 2. And 1/2 negative square root of 3 over 2. All right, and so that's going to give me, again, they're not at any type of interval that's consistent, so you need 2 different formulas, which is pretty typical in trig. So this is what, pi over 6, 2 pi over 6, so pi over 3 plus 2k pi. And then the other one would be pi over 6, 2 pi over 6, 3, 4, 5, 6, 7, 8, 9, 10 pi over 6, which reduces to 5 pi over 3 plus 2k pi. All right, now, those are my general formulas. As far as answering the question, you know, kind of depends on what interval they give you. But if they give you the interval, say, you know, like 0 to 2 pi or something like that, I could sub in 0 and get all those answers. So I could get pi over 3, 5 pi over 3, and pi over 2. If I sub in k equal 1, all of these are going to be over the 2 pi limit, so I'm done. So those are within that domain. This is the general formulas.